Hello viewers, welcome to my channel. So today we'll be discussing about traveling salesman problem using branch and bound approach. So in the last video we discussed about brute force approach, which is the traditional method. Now we'll be looking into identifying the optimal solution for traveling salesman problem using one of the techniques called as branch and bound approach. So in this video I'll be discussing the steps involved in branch and bound and followed by the next video with an example. So before discussing about the approach, let us have a recap of the objective of traveling salesman problem. So the objective of traveling salesman problem is to find the shortest possible tour by visiting each city exactly once and return to the same city. So you have to start at a particular city and then you have to visit all the other cities exactly once and again return to the same city where you have started. So this tour should be nothing but the minimum cost tour. So that is what the objective of traveling salesman problem is. So now we'll be looking into the branch and bound approach. So coming to the branch and bound approach, the first step is that initialization. So any algorithm has an initialization part, which is nothing but the primary step. So in this initialization, what you have to do is first you have to build a distance matrix. Distance matrix is nothing but you'll be starting at a particular city, which is the primary city, which is represented by I, and you'll be visiting all the other cities that are represented as J. So D of I comma J means I represents the starting city where you start from, and J represents the every other city that you are going to be visiting from this first starting city. So that is what the first step is. So you have to define the distance matrix D. Dij, where I represents a city I where you are starting from, and J represents every other city that you are visiting. And next second step is that one is you have to initialize a distance matrix and the other is you have to initialize a priority queue. Priority queue is nothing but based on the highest prioritized nodes that you are including in the search tree. So here in this branch and bound approach, the branching happens by building a tree, which is nothing but a search tree where you will be starting from a particular node and you have to visit every other node and you have to identify the optimized tour or the minimum cost tour. So that is what priority queue is initialized. So first is you have to initialize a matrix, distance matrix, and second one is a priority queue in order to manage the nodes of the search tree. So you have to start with an initial node and then you have to cover every other cities. Then you have to start building the routes or the paths or tours from that particular starting city to each and every other city. So this is what initialization is. Now moving on to node representation. So as we know that every node in the graph is nothing but the city we are representing in this traveling salesman problem. So each node in the search tree represents a partial tour. So you'll be starting at a particular city. For example, in the previous example, we have taken a graph like this A, B, C, D. So you are having a graph. You are starting from A and you are traveling to B, to D, to C, and again return to A. So here every node is nothing but a partial node because until and unless an entire tour is completed, every node is represented as a partial node. So when we are starting from A, it is reaching to B, it's a partial tour, and again from B to D, it's a partial tour, and again from D to C, it's a partial tour, and once in returns to the A, then the complete tour is being established. So the node representation is nothing but in the search tree. So you'll be building a binary search tree where every node is represented, and finally you will be identifying the tour. So every node is nothing but a partial every node in this tree represents a partial tour. So the partial tour is nothing but, I said that you will be starting at a city, when you move on to B, this is one partial tour. When you move on from A to B, B to D, this is a partial tour. And when you move on from A to B, B to D, D to C, it is a partial tour. And once it returns to that same city, then the complete tour is established. Till then, every node in that search tree represents a partial tour. So these nodes include the current partial tour, the current cost of the partial tour, so how much distance it has been traveled, and next level, how many number of cities it covered, and reduced distance matrix, we'll discuss what reduced distance matrix is, and the lower bound of the node, how these two are calculated, we'll be looking into the next steps. So the second step is that each node in the graph or in the traveling salesman problem is nothing but a representing a partial tour. This node includes partial tour, cost of that partial tour, how much distance it has traveled, level, how many number of cities it has covered so far, reduced distance matrix, and lower bound of the node. So this is what every node includes. So we are starting at A, then again covering all the other cities and returning to the same city. So that is what so far we will be looking into. And next, moving to the third step. So the third step is to calculate reduced cost matrix. So the main motto of this step is that it gives the lower bound of the root node. How this cost matrix is being calculated. So you have to eliminate the smallest element or subtract the smallest element in each row. Once every row is being finished, then you have to start subtracting the smallest element from each column. So the reduced cost matrix is built by subtracting the smallest element from each row and then subtracting the smallest element from the each column. So that gives the lower bound of that particular root node. Root node here currently is A. So we'll be starting calculating the lower bound of this root node by eliminating or subtracting the smallest element in each row and each column. So that is what the third step is. So far first three steps are, one is initialization, where you have to build the distance matrix and you have to initialize a priority queue. Next, second is node representation. So in the search tree, every node is represented with a partial tour. And next, third one is to calculate reduced cost matrix. So this gives the lower bound of the root node. So these are the three steps. Now moving on to the fourth step, which is important part, branching. So since this is a branch and bound approach, branching in the sense you are building a tree. So you have to build a tree where every node, where you'll start at a root node which is considered as a starting city, and every other node, every other tour is being built by considering the every other cities as the child nodes. So to the B again, the child node will be D, and so on. So that is how you will be building the tour. Now in the branching step, select the most promising node, that is the node with the lowest bound from the priority queue. So once your priority queue starts building from the starting city A, then moving on to including B, then so on. So you have to build this search tree in such a way that the child nodes will be selected in such a way that the child node should have the least lower bound. The city or the node one which is having the least lower bound, so that will be added into the priority queue. So initially I have started the priority queue with A because that is the starting city I am including. Then you are visiting B. If at all the calculated lower bound of this B is less than the root node, then you can include it. Same again, you are moving to next C. If you are calculating the lower bound of C and it is again less than the reduced matrix, then it will also be included into the priority queue. So this branching should be done in such a way that you have to identify the node with the least lower bound. So the formula for this is total cost is equals to parent matrix cost plus reduction cost plus path. So reduction cost is nothing but you are subtracting the smallest element from each row and each column. And parent matrix cost is initial root cost. So the root node that you have selected, so that matrix cost. Next is reduction cost once you started visiting each and every other node. And the path, the distance cost, the cost of the city which you are visiting from the initial city. For example, I am taking A to B. So the path includes the cost of this. So the cost of this A to B. So that is how the path is included. Path is nothing but cost of the path from the primary city to the city you are visiting. Reduction cost is elimination of the smallest elements and from the each row and each column once a distance matrix is built between these two nodes. So that is what the formula. This formula is very important. Total cost is equals to parent matrix cost plus reduction cost plus path. We will be discussing this in detail in the example. You will be knowing how to calculate this. And next, moving on to the next step, that is calculate the lower bound for each node. So like I said, in the priority queue, after you are including each and every child node that is having the lowest bound, so this lower bound has to be calculated until an entire tour is built. So for each and every child node you are including, you have to calculate this lower bound. So that has to be smaller than the parent matrix cost. So that is what lower bound is. Next, bounding. So if the lower bound of the node is greater than or equal to the current minimum tour cost, so whatever the parent matrix cost is there, if at all you are calculating the lower bound for any particular child node you are including in the priority queue, its lower bound, if it is crossing the cost of this parent matrix cost, then you have to eliminate that particular child node. So that is what this step is saying. Branching is to start building a search tree by including every child node having the least lower bound. So if that lower bound is being maximized, or if it is maximum or greater than the parent matrix cost, then what you have to do, you have to prune that node. In the sense, you should not include that child node into this priority queue. If any of the visiting city, or if any of the node that is being visited having the lower bound greater than the parent matrix cost, then it has to be pruned, which means it has to be removed. Otherwise, if at all it is okay, if at all it is meeting the conditions, then it can be added to the priority queue. So that is what bounding is, branching and bounding. Okay, next, moving on to the next step, which is nothing but repeat. So you have to repeat these steps until a complete route is being identified or a complete tour is built. So select the next promising node from priority queue and repeat the branching and bounding steps. So you have to include the nodes in priority queue having the least lower bound, and if it is crossing the parent matrix cost, then you have to prune it or delete it. So that is what the next step is. You have to repeat these steps until and unless the condition is met. Next, eighth step is that if a node represents complete tour, compare its cost to the current minimum tour cost. So once the entire tour is built, you have to calculate the entire distance cost and you have to compare its cost to the current minimum tour cost. So if it is lower, update the cost and it becomes the best tour. So you have to repeat these steps until a complete tour is built. Then you have to check if the tour is having the minimum cost. For us, for example, A to B, B to D is the tour that I have completed, and again D to A, and again it reaches D to A. If this is the tour I have completed, then you have to check the calculate the distance of this entire tour, and you have to check if it is less than the parent matrix cost or the current parent matrix cost. So if it is meeting the condition, then you can update that cost and you will consider the tour as the best tour. Now next, last step is to terminate. So the algorithm terminates when the priority queue is empty or complete tour with minimum cost is found. So this algorithm runs until the entire priority queue is empty. So you are choosing each and every node that is having the least bound and you are including it into the search tree and you are building a tour. Once all these nodes from the priority queue are emptied, or once a complete tour with the best minimum cost is built, then this algorithm stops. So that is where the algorithm terminates. So let us have a revision of these branch and bound steps. So one is that you have to initialize a distance matrix and a priority queue. Next, node representation. There will be a starting node you will be starting the tour from, and you will be visiting every other city exactly once. So until the entire tour is completed, every tour is considered as a partial tour. So these nodes includes partial tour, the cost of the partial tour, the level, that is how many number of cities it has visited so far, the reduced distance matrix. Reduced distance matrix is nothing but you have to subtract the smallest element from each row and each column. Next, the lower bound of the each node. So you have to calculate the lower bound of each node. So these all are included in a search tree. Next step is that you have to start branching. So that will be done by using the formula total cost is equals to parent matrix cost plus reduction cost plus path. And next step, you have to calculate lower bound for each node that is present in the priority queue. So next is bounding. If any of the node in the priority queue is holding the lower bound which is greater than the parent matrix cost, then it has to be pruned. That means it has to be removed. If at all it is meeting all the conditions, or all the conditions are satisfied, then it can be included in the priority queue and then can be used in building the search tree. And next, repeat these steps until all the nodes are being covered and a complete tour is being built. Once the tour is being built, you have to compare if the cost of the current tour is minimum than the parent cost matrix tour, then that will be included as the optimized solution. And terminate, that is nothing but your algorithm terminates once you identify the best minimum cost tour and the priority queue is empty. There are no nodes present in that priority queue. So this is what branch and bound algorithm is. So I'll be looking into the example in the upcoming video. Thank you.